All right, so in this video, we're going to look at some surprising connections between some functions that you're familiar with, and we're going to derive one of the most famous formulas and most useful formulas in all of mathematics, known as Euler's formula. All right, so what I wanted to remind you of, first of all, is that we had, when we talked about Taylor series, we derived Taylor series or power series representations for some simple functions like cosine of x, sine of x, and e to the x. Now, what was interesting about these is that the cosine of x series has only even powers of x. The sine series has only odd powers of x. And e to the x has all of the powers of x. And when you look at the denominator of all these terms, what you'll see is that each denominator is the same as the exponent with a factorial, right? So x squared goes with the 2 factorial. If I write this correctly, that is, x cubed goes with a 3 factorial, x to the 4th goes with a 4x factorial, and so on. And given that the cosine has all of the odd or all the even powers and the sine has all of the odd powers, it stands to reason that maybe there's some connection between sine and cosine and e to the x. And it turns out that that is actually correct. And back in the 1700s, one of the greatest mathematicians of all time, Leonard Euler, proved the following result, that e to the ix is equal to cosine of x plus I times the sine of x. Okay? So this is known as Euler's formula. Now that's a remarkable result because sines and cosines are functions that oscillate, and the exponential function is one that we usually think of as growing very, very quickly. And yet somehow there's this very deep connection between them. And so what I want to do in this video is actually prove that that's correct and see how we can do that using infinite series. All right, so let's do that. Let's find a Taylor series for e to the ix. And just as a note, when I write I, I'm referring to the imaginary number I, which is the square root of -1. Okay? So I'm taking the imaginary number I times x, and since this is related to the exponential function, if we want a Taylor series, all we need to do is we need to plug in ix everywhere that we see an x. And so our summation should be n equals 0 to infinity of I times x to the n all over n factorial, which is equal to, all right, let's simplify that just a little bit. So we have I to the n times x to the n over n factorial. And what is I to the n? Well, if you take the square root of -1 to the 0, well, that should just be 1, right? Anything to the 0 is just 1. If you take the square root of -1 to the 1, you get, well, I, right? If you take the square root of -1 and square it, well, the square root of something, or the square of something that's already a square root, should just give you the thing inside, and so that's going to be -1. And if you take root -1 cubed, well, that's the same thing as multiplying the -1 times I, and so that's -I. And if I take root -1 to the 4th, well, that's the same thing as taking root -1 squared and then squaring it again. And so that's going to be -1 squared or plus 1. And so you'll notice that this series, if I plug in, for my first term, I'll have, when n equals 0, I'll just have a 1 for my I to the n. And then I'll have x to the 0 over 0 factorial, so just 1. When I plug in n equals 1, I will have I times x over 1 factorial. And then the next term will be, we'll have I squared, which we said was -1. So it'll be negative x squared over 2 factorial. The next one will be negative I times x cubed over 3 factorial. And again, I'm just plugging in these products there to simplify the a to the n term. Everything else is just like the regular e to the x. Okay, and so after that, I'll have x to the 4th over 4 factorial, and then I'll have plus I times x to the 5th over 5 factorial, minus x to the 6th over 6 factorial, minus I x to the 7th over 7 factorial. And we could go on as long as we want, but what I want you to notice is that we're alternating between the things that have I and things that do not. And so given that this is a convergent series, which we won't prove this for the complex numbers, but it is indeed convergent, uh, we can rearrange this a little bit. In fact, it's absolutely convergent. So let's rearrange the terms and group all the terms that have i's together and all the terms that do not. And so the terms that do not have i's are going to be 1 minus x squared over 2 factorial plus x to the fifth, x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on. And so notice all of the even powers are going to show up there. Plus, now we'll look at the I terms. And since they all have an I, we can factor that out. And what we'll be left with is there's one, we'll have an x. The next one is in negative x cubed over 3 factorial. The next one after that is in x to the fifth over 5 factorial. Then minus x to the seventh over 7 factorial. And so on. And you may recognize those two terms in parentheses. The first one is just the Taylor series for cosine of x, and the second one is just the Taylor series for sine of x. And so this must be equal to cosine of x plus I sine of x. So isn't it amazing? The exponential function is equal to a cosine plus the imaginary number root negative 1 times the sine of x. And once you've got that equation, you can start to come up with other interesting results, like, let's say, what is e to the I times pi? Well, we know how to compute exponentials of real numbers, but now we can compute exponentials of complex numbers, because we're just going to take the cosine of pi plus I times the sine of pi, which is equal to, well, cosine of pi is equal to negative 1 plus I times the sine of pi, which is 0. And so there we go. E to the I pi is equal to negative 1. Or sometimes you'll see it written this way. E to the I pi plus 1 equals 0. And that equation is interesting because it includes what are arguably the 5 most important numbers in all of mathematics: 0, 1, I, pi, and e. Ties them all together into one neat equation. All right. So that's another neat application of Taylor series. They allow us to derive this formula, e to the ix equals cosine x plus I sine of x. And although that may seem like just a odd fact, it turns out that's one of the most useful formulas in all of physics and engineering, because it allows us to take problems that involve oscillation with sines and cosines and write them in terms of exponentials, which greatly simplifies the calculations and allows us to come up with nice, concise ways of describing electrical currents, waves such as sound and light, and many, many other things. So it's an incredibly powerful and very practical tool. And if you go on in math or science, maybe you'll encounter some of the applications of it.